I want to do an example of conservation of angular momentum. This is one of the three great conservation laws: momentum, angular momentum, and energy of classical physics. And conservation of angular momentum behaves a lot like conservation of momentum in some ways, but with the extra twist that we've got to figure out, angular, with the extra twist that we've got to figure out how the angular momentum works instead of just directly looking at how something's moving. We've got to work out what those rotational things are. This example will give us some good exposure to all those techniques we need to use. In particular, I'm going to steal a scene from the extended edition of the Lord of the Rings Return of the King movie. This scene is rather reviled by Tolkien purists because it has nothing to do with the scene in the books. It kind of undoes some important things. But you don't need to hear my Tolkien rant. You were here for the physics. The scene is this. The evil, treacherous wizard Saruman has fallen from his tower of Orthanc and Isengard, and he's falling down, and he falls onto a spiky wheel and impales himself on the spikes in the wheel. This is probably why it wasn't in the main movie. And he impales himself on the spikes in the wheel, and the wheel sort of turns, and he's ground under or something. So this is the story. He's falling down, he hits the wheel, and the wheel starts to turn. I want to know, given this information about his speed just before he hits, 30 meters per second, and the location where he hits the wheel, we'll put that in a picture in a second to make it clear, but half a meter horizontally from the axle and a bit above. His mass, 50 kilograms. The wheel, which we're going to model as a solid disc of radius 2 meters and mass 1,500 kilograms. And I want to know what is the final rotational, or the final angular velocity, or at least the angular speed, the magnitude of the angular velocity, of this wheel with Saruman stuck to it after he hits. We're going to assume the wheel was sitting still to begin with, and it starts to rotate once he gets on there. All right, so let's ask that question. To do this, to address this, in almost any physics problem, our first step is to draw a picture. And for a conservation law problem, our first step is almost always to draw pictures for before and after. So my before picture, immediately before the collision, this is a collision situation. It's something where there's a fast thunk of Saruman hitting the spiky wheel, where immediately before and immediately after, in between those two, the biggest thing going on is the collision itself. We're going to assume that means that this system is, on a rotational level, functionally isolated from the outside world. There's an axle, it's a low friction axle, and even though there probably is friction and stuff going on, during the collision is the biggest thing going on, so we can ignore all the other stuff. So okay, here's my before picture. I've got Saruman, forgive my artistic skills, I've got Saruman falling. Let's see, he's a wizard, he must be wearing robes or something. Robes. Saruman is falling down with speed v, or velocity v Saruman initial of 30 meters per second. I guess that's already labeled here. I'm not going to put all my numbers up here. I'll put my numbers in a table. You figure out how you want to do things as you set up a physics problem. So v Saruman initial, and underneath him is the spiky wheel. Here we are, one spiky wheel coming up. Spikes, got to get some spikes there, make sure it looks deadly. Obviously, the assumption this is a perfectly uniform, solid disc is not quite right because it has spikes, but we're going to approximate it that way. It has its frictionless axle here at the center of the wheel, and what we're told in the setup is that he hits at a 0.5 meters horizontally from the axle. What that means, how you're supposed to interpret that is that if you were to follow his downward path over, this distance here is 0.5 meters. I don't know if you can quite read that, that's too small. But that distance is, if I call it the horizontal distance h, his horizontal distance h is that 0.5 meters, and the radius of the whole wheel, I'll call capital R, will be the 2 meter radius that was given in the problem. Saruman has a mass little m, the wheel has a mass big M, little m, and so I've labeled things. You can see already that I'm labeling things as I go in here. I'm developing symbols for all the things I'm drawing. And for my after picture, I'll see if I can fit it down here. My after picture is simpler because it just has the spiky wheel, spikes, you get the idea, one spiky wheel, and it's got, I guess, an impaled Saruman over here, impaled Saruman over here, and we have then, it's rotating with some omega final, some final angular velocity that we expect the whole system to be rotating around that central axle. So there's my before and after. I guess I could say omega wheel initial equals 0, just to make it clear that it's not moving initially. Okay, so I've got my before and after pictures, and it's a good idea to make a list of known and unknown quantities that we have in our system. So collecting data, I know the magnitude of Saruman's initial speed is 30 meters per second. I know its direction is down. It's straight down. I know that, I guess probably I should develop some sort of coordinate system along the way. So maybe the best coordinate system to use to express that as a vector is going to be something with the origin of the coordinates at the center of the axle of this wheel so that the rotation is around that point. That's the natural thing you do. So I'm going to choose coordinates so that I've got an x here and a y here. Z would be out of the board, I guess. And so I guess I can translate this into just a vector. B Saruman initial is 0 minus 30 meters per second, 0, as a column vector. So that's maybe a bit more explicit. That gives me, instead of being a magnitude and a direction, I can be explicit with a column vector. We'll see if we need that later. Thinking about physics problem solving, I actually haven't thought through exactly which of these things I'm going to need, exactly what form I'm going to write this in. I'm just trying to be explicit. I know it's useful to have coordinates chosen. I know what my origin point is for rotational stories, so I've done that here. What else do I know? I've got a list of things. I know I've written that the mass of Saruman is 50 kilograms. Big M for the wheel. I guess I didn't call it Saruman. I just said mass of Saruman is little m. Big M for the wheel is 1,500 kilograms. The radius of the wheel is 2 meters. That distance h is half a meter. That horizontal distance h from Saruman's path over to the axle is 0.5 meters. You can see that he's going to also be some distance y up. I just haven't specified that in the problem statement. So I've got that. What else? I've already got that. Omega wheel initial equals 0. Okay, that seems to be a lot of stuff. Those are a lot of my known quantities. My big unknown quantity then is what is omega final, and I don't know that. So okay, because the system we argued was functionally isolated, for rotation around the axis of the center of the wheel, because it's functionally isolated, we will use conservation of angular momentum. Conservation laws are wonderful. We get to use them. I'm happy. So, okay, what are we going to do? How do we use conservation of angular momentum to solve this problem? Well, I guess I have to figure out what my initial angular momentum is. My system is Saruman and the wheel. Those are the pieces of my system. So L total initial is going to be L of Saruman initial plus L of the wheel initial. The wheel's not even moving initially, so it doesn't have any angular momentum to begin with. So that's 0. And Saruman's angular momentum, we're going to model Saruman as a particle falling down. Maybe that's a bad model if we want to really be careful, but it won't be too bad. We'll model Saruman as a particle, and we'll say that that is angular momentum for something we're treating as a particle is R Saruman initial cross P Saruman initial. R cross P. radius vector cross product with momentum vector. And yeah, I can draw this in. I guess when Saruman hits there, his radius vector from the origin to where he hits is here, R Saruman initial. That's his radius vector going from the origin to the place where he's going to hit. Cool. I've got that. And his momentum, I guess I better write this down. P Saruman initial is mass of Saruman times V Saruman initial. And we can just multiply it in. His mass is 50, if I want to put in the thing, his mass is 50 kilograms times negative 30 meters per second. This would be 50 kilograms times 0 minus 30 meters per second. 0 vector would be 15 minus 1,500 kilogram meters per second. That looks like a vector to me. Or I could just call it mv. I could have written this as 0 minus m vs initial, mass times the initial speed, and done it symbolically that way. But whether I do it with numbers or symbolically, I've got a value for p as a vector. I know its direction. And I guess for r, that r Saruman initial, let's look at that for a second. R Saruman initial equals, this is one where we'll be able to do the calculation in a couple different ways. What do I know about it? I guess I could figure out the height based on the Pythagorean theorem, solve for the unknown leg of this right triangle. I know that it's going to be an x component of h, that horizontal distance, a y component of, I don't know, y initial and 0. I don't know what that y initial is. That's an unknown thing. I could solve for it. We'll find out that I don't need to solve for it. So I'm not going to bother right now. It would be the square root of 2 squared minus a half squared, I guess. But we can dodge the need to solve for that entirely, and we'll see how. I've got these two things. Let me find that initial initial momentum then. Let's see. I'm going to erase the problem statements since we don't need that anymore. I'll, in fact, go all the way up. We don't even need the label anymore, probably. I'll just get rid of that. What I'm going to do, to find the angular momentum, then I need to take the cross product of those two vectors. And I guess, first of all, before I do calculations over here, let me just draw the two vectors over here and see what we have. My r vector, remember, points, my r vector points like this. Oh, hang on, I've got my colors backward. My r vector points like this, r, and my p vector, my momentum vector, points straight down. Those are my r and p vectors that I've just drawn. And so I guess this angle here is the theta between the two, the angle between the two vectors. And that's the cross product that I'm taking. The angular momentum is the cross product of r cross p. One thing I can do is just look at the direction of this. And I can say, well, the direction of r cross p is perpendicular to both r and p. Since they're in the plane of the board, that means it'll be into or out of the plane of the board. And which one? Well, I use the right-hand rule. My favorite right-hand rule, I stick my fingers along the r vector, rotate my wrist so when I curl my fingers, they go toward the p vector, and now my thumb goes into the board. So I know that L initial is going to be into the board. That's my conclusion, that I know that'll be the direction based on the right-hand rule. So, okay, I've got that. How would I find the actual value for that initial angular momentum, the magnitude of that? Well, a couple ways I can do it. I know that the magnitude of angular momentum is equal to the magnitude of r, I'll be explicit, r Saruman initial, times the magnitude of Saruman's momentum, p Saruman initial, times the sine of the angle between them. The sine of the angle between them is kind of tricky, right? How am I going to find that sine of the angle between them, sine of this theta? It's a bit of a pain, actually, to do this precisely. However, it turns out there's a trig identity that could help us with this. It turns out sine of theta is the same as sine of 180 minus theta. If you think about the graph of sine that starts, a sine graph starts at 0 and goes like this. This is 0, this is 180. So sine of theta is equal to sine of 180 minus theta. If you think about that graph, that means that whatever, this is kind of silly, but to go through all this length of talking about it this way. But let me just, here's my R, let me just draw up here what I'm thinking of. This angle is 180 minus theta up here. And this right triangle has that 180 minus theta in it. And so the opposite side from that is my horizontal distance. So in fact, from my picture, I happen to know that R, the magnitude of R times the sine of 180 minus theta is equal to my horizontal distance over, that half a meter. So I've got that, excuse me. I've got that horizontal distance going. This is a little sneaky. This is really the perpendicular distance. This is, you see a lot of books talk about this. This is how much of the radius vector is perpendicular to the momentum. It's that part, r sine theta. And so in this equation, and this equals sine of theta, so in this equation I can write that the magnitude of the initial angular momentum is going to be h times magnitude of Sauermann's momentum. We could get that another way too, just in case that was unsatisfying. You're saying, what is he doing here? Remember, we can also do a cross product of these vectors in components. I could have said, or I could have instead said that my cross product, I know that L initial vector is equal to the R vector, which is h, and the unknown yi 0, cross product with, and my P vector is 0 minus m v initial 0. This is the cross product that I could write down, and there's just an equation for that, remember. The equation for cross product in components is, let's see, for the x component it's y pz minus z py. Here it is z px minus x pz. If you do physics for 20 years, you'll be able to memorize this too. And x py minus y px. If you know that equation, then I can look at this and say, oh, in my case, we don't have any z components of anything. So this is 0, and this is 0, and this is 0, and this is 0. And so all I'm left with is 0, 0. And then down here, my x is h, and py is times minus m v initial magnitude minus y, which is y initial, px is 0. So that's a vector, but this term is just 0 anyway, and I get L initial vector is 0, 0 minus hm speed initial, and that's actually the same thing I got before. This one is m times the initial, hm v initial, and this just tells me it's in the minus z direction. So okay, the long ways of getting to this point. I knew what this was going to be. Into the board is my minus z direction, because in the usual coordinates x and y, a right-handed coordinate system means that the z direction is out of the board, plus z is out, so minus z is in. So these agree with each other. However you care to find that initial angular momentum, we have it now. We have it as a vector, in fact, in component form. So we've got that. What's the final angular momentum? So that's a value. It's into the board. Check, reasonableness check. When he hits here, and into the board angular momentum corresponds to rotation this way by the right-hand rule. I put my thumb into the board and curl, and that's the way I expect this wheel to turn if he hits on the right-hand side of the wheel as I've drawn it. So okay, this feels good to me so far. Let me keep going then. I'm going to come over, I'm going to leave my pictures here and leave my numbers here. I know I'm using a lot of board space, but let's see where this is. I've got my L initial all added up. L final, I'm now an object rotating around a central point. I'm rotating around a fixed axis of rotation, in fact. So I will go so far as to say that L final is equal to the total moment of inertia about that fixed axis times omega final. It's a little dangerous to say that when I don't have a perfectly symmetric situation, but I think it's going to be fine. So we've got this story. I total is just I of the wheel plus I of Saruman stuck to the wheel times omega final vector. And so what are those moments of inertia? Well, for a solid disk, 1/2 mr squared is the moment of inertia of a solid disk. For Saruman we're treating as a point particle, kind of iffy, but we're treating him as a point particle. Yeah, it's dubious, but point enough. And for a point particle, remember the moment of inertia around a point, at least if it were symmetric, or waving your hands a little, is going to be little m times the distance squared, r squared, because he's a distance r away from the center in that picture, times omega final. And so this is the point where I can just plug some stuff in. I can go in here and say that this is equal to 1/2 times 1,500 kilograms times 2 meters quantity squared plus 50 kilograms times 2 meters squared. The 50 is not going to be all that important. Times omega final. And I'm sure I've done that calculation here, so I don't need to do it while you stare at me. No, brilliantly, I haven't done that, so you don't have to watch me stare. So you don't have to stare at me. So let's go ahead and do it. 750 times, let's see, 1,500 times 4 divided by 2. That gives me 3,000 kilogram meter squared. Doesn't need to be up high. 3,000 kilogram meter squared plus 50 times 4 is 200. Yeah, kilogram meter squared times omega final. And my left-hand side, I already had, I think, something there. That this was my L final equals, and that had to equal L initial vector, which was this thing, 0, 0. So this was 0, 0, and then minus 0.5 meters was my h, times the mass of Saruman was 50 kilograms. I probably could have done some of this symbolically. And his initial speed was 30 meters per second. That's supposed to be up there. Okay, so multiplying that together, 50 times 30 times a half comes out to be 1,500, 750. 0, 0 minus 750 kilogram meter squared per second. Those are units of angular momentum, so that makes me happy. And so this total, I guess I could have written down the total, couldn't I? This total here was 3,200 kilogram meter squared. So all I need to do to find my omega final is just divide sorry for the ding there. All I need to do to find my omega final is just to divide those two things by one another. I'll find that omega final vector is equal to L final divided by, well, same as L initial, really. L final divided by 3,200 kilogram meter squared, and this equals L initial divided by 3,200 kilogram meter squared. What do we wind up with then? Our final number ends up being, this is 0, 0, and then minus 750 kilogram meter squared per second divided by 3,200 kilogram meter squared. Oh, this is kind of ugly. But when I get down to it, you can already see 715 is going to be a little less than a quarter, I think. How'd I do? Well, I should pull out a calculator, I suppose. You can see the kilogram meter squareds will cancel out. So this comes out to be 1 over seconds. That's good because that's the same as radians per second. Radians are a sort of ghost unit. So what do I have? I have You know, I'm going to pull out a calculator. Excuse me for 1 second. Forgot my calculator, my goodness. How can I forget that? I wind up with 750 divided by 3200. I get 0.23, 0.23. Hope I got that right. I get 0, 0 minus 0.23 radians per second. It's 1 over seconds is the units I get, but remember radians are, once I'm talking about angular things, radians are what I have. So I've got that 0.23 radians per second, and that is my final angular velocity. It's negative. It's negative in the z direction. It's a z component negative, so that means it's into the board. I interpret it with the right-hand rule. Thumb into the board. The direction of rotation is this way, and there we have it. It's going the way we expected, and we got an answer here. My only concern in having written this down is that in my notes, the answer I got was exactly double this, and so that's a fascinating question. I had found earlier why not negative 0.47 radian per second in my notes. This is what happens when I go a little bit off script and do things a slightly different way than I've written down. And that's a great question. These are always the double check. Both of these look generally reasonable. It's going to be a slow rotation. You know, half a radian per second is not very fast. A quarter of a radian per second is even slower, but it is a very big, heavy wheel. So this makes sense. I think it would not be interesting on this video for you to watch me try to figure out which of these two numbers is right. So I think maybe I'll just leave you to ponder whether there's something that I have messed up in writing this down. Maybe I can check this really quick just to see. 1500 times, yeah, no, nothing's obvious to me. I think I will leave this as one of the mysteries of the ages, why my notes had this different number in them. And maybe if I spot a problem or if I spot how to fix it, I'll put a note in the comments on the video. But in any case, the method used here is, the method that I used in solving this is the method you'll use for any conservation of angular momentum problem. You set up a before and after, you figure out the angular momentum either by doing a cross product, R cross P for things that are that are acting like point particles, or by doing I omega if you've got a fixed axis of rotation, and then from there, you just set initial total equal to final total, and that'll find that'll give you the answer to your question, or at least if you don't make any math errors, it will. I hope that's helpful in setting up your problem, and hope you understand angular momentum problems a little bit better.